Okay, thank you for the introduction. I took the liberty to slightly modify the title of my talk. So, like that. Yeah, I'm gonna tell you about our work on chirals and frequency generation, but I'm gonna give you a broader overview of the things that we'll be working on recently on ultrafast molecular chiral recognition. So the ideas that I'm going to present are strongly connected to Andres just presented, but I'm going to focus most on chiral analysis rather than manipulation and photochemistry. And I want to start by thanking the Darek and the organizing committee for giving me the opportunity of presenting my work here. And I thought that the best way that I could thank Darek is to start my presentation with a picture of him and a question for you. So you can scan this code and answer the question whether you think if Darek is chiral or not. And while you do this, I am not going to tell you what chirality is, but I do want to remind you of the key principle for chiral recognition, which is that opposite versions of the same chiral object can only interact differently if they interact with something that is also chiral. And this other chiral object can be anything. It can be another chiral molecule, it can be chiral surface, it can be chiral light, or it can also be non-chiral light, but in a setup, in a way that the combination of the whole thing becomes chiral. And if you want to learn more about this, Andres and Olga presented this in this paper, and we recently wrote a perspective where we describe this thing. So let's see if people answered this. Okay. Okay, so 3 people that don't care about this. So the answer is no. Well, let me go back. Let's see if I could get more. No, Darek is not chiral. So Darek's hands are chiral, and it has left and right hand, but Darek has a mirror symmetry, has a plane of symmetry. So basically the chirality of his 2 hands cancel out because they have opposite chirality. But Darek is an example of a structured chirality because he has chiral hands, and the way that he structures his hands in space is important. And I'm going to show you now how by structuring light in space we can create optical fields that have the same structure as Darek. And I'm going to show you also that this is not the same as this. So, why should we care about chirality? There are a few people that say that they don't care. I guess they mean that they don't care about Darek being chiral, but they care about chirality because chirality is everywhere. Chiral molecules are ubiquitous in nature. Most biomolecules are chiral, and one example where chirality plays key roles is in the pharmaceutical industry. So you can have an enantiomer, like the left-handed enantiomer of methamphetamine, which is a nasal decongestant, and then the right-handed enantiomer, which has a very different effect. And this is actually quite important because over 70% of the drugs which are currently in use are chiral molecules. In most cases, the differences are not as dramatic, but it is still very important to distinguish them and to separate them. Other examples of the importance of chiral molecules are they are now well established as a chiral biomarker, so it's now established that abnormal values of the enantiomeric excess on some biomolecules are correlated to cancer, kidney, and brain diseases. They're also very important for molecular rotors or spintronics. So this is the structure of my presentation. I'm going to explain why circularly polarized light, which is the standard chiral tool, is not ideal. Then I will present the idea of local chirality, which is strongly connected to what Andres presented. And then I will tell you how we can structure chirality in space to have optical fields that look like Darek and even more complex optical structures. And then I will tell you about our work on some frequency generation. So, traditional spectroscopy uses circularly polarized light as a chiral reagent. So you have left and right-handed versions of the same chiral molecule, and you make it interact with a circularly polarized field. Then you measure the spectrum of absorption, so you basically measure the number of photons which are absorbed as a number of the wavelength. And these 2 spectra can be different because you have chiral molecules interacting with chiral light. In practice, they are not very different, and sometimes it's quite challenging to see the differences because they are below 0.1%. So this can be resolved, but it creates challenges, it creates limitations. If you want to do ultrafast spectroscopy, this is very challenging. If you want to do measures in a very dilute sample, it's also very challenging. If you have a sample with many different chiral molecules and you want to detect chirality simultaneously, this is even more challenging. So to overcome these challenges, we need to understand why the differences are so small. And as Andres explained, circularly polarized light is chiral because it makes a helix in space, but the pitch of this helix is orders of magnitude larger than the molecules. So the molecules don't feel this helix. What the molecules actually feel is the local polarization of the electric field vector in one point in space. And this makes a circle, not a helix. And circles are not chiral. So if you want to get chiral effects from this field, you need to go beyond the electric dipole approximation. You need to include magnetic effects. And as Andres explained, these effects are very, very weak and are not balanced. And this is the reason we have such small sensitivity. So this brings me to the idea of locally chiral light. Again, I'm going to emphasize this. This is the polarization of the electric field vector of a circularly polarized wave in one point in space. And it does not make a helix. It makes a circle which is not chiral. But what if we twist this circle? We can twist the circle and have something like this. You can have a field that looks a bit, where the Lisa U figure of the electric field, it looks a bit like some sort of potato chip. And this potato chip is chiral, and you can create these fields with two ingredients. But I'm going to emphasize that this is fundamentally different for circularly polarized light, because circularly polarized light is chiral in space, but it's not chiral when you look at it locally in one point in space, where this field is chiral already within the electric dipole approximation in one point in space. So to create these fields, you need two or more frequencies. Andres talked about having 3 frequencies. I'm going to remain in 2 frequencies, which is the minimum requirement. And I would say that this is relatively easy using current technology. And of course, you also need 3 orthogonally polarized electric field components, because if you only have 2, then the polarization is going to be planar. This is not so straightforward, but it is possible, and there are several ways that this can be done. We can do this using non-collinear laser beams, and I'm going to talk about this in a minute. You can also have one laser beam, but in a way that you make it very, very tightly focused, like sub-wavelength focus, and then the field, because of confinement, acquires a longitudinal component. And you can use this for creating locally chiral light. Or you can go to nanophotonics, and here by structuring matter, you can structure light, again, thanks to confinement. So I'm going to talk about using non-collinear laser beams, and this field can be generated with this non-collinear setup. So this field, you have, the pointer is not working, but you can see that it is elliptically polarized on the plane that is at the bottom. And by the time that you make one ellipse at the fundamental frequency, you go up and down twice. So this field is polarized at frequency omega, the fundamental frequency, in one plane, and it has a 2 omega field which is orthogonally polarized. So if you use this setup, by combining the fundamental fields which are on the plane of the screen, thank you, Derek. Yes, by combining this field and this field, because the 2 beams propagate non-collinearly, when you add them together in the region of overlap, you get something that is elliptically polarized. And with these components, you create the ellipse. Now you have the 2 omegas here, which are orthogonally polarized, and this gives you the up and down. And that's how you can create a potato chip field. It's not so straightforward, and I'm going to describe this because we need the beams to be non-collinear. So this plus this is not linear, it's elliptical. But by having them non-collinear, that means that the 2 beams are going to arrive at the same point with a delay. And that means that you are going to have a phase delay between the frequency component, which can change the properties of the field. Okay, so I'm going to tell you now how we can structure this to make direct light. So this is the non-collinear setup that I was describing, and I'm going to show you how the chirality can change along this direction, because the beams come at an angle and this induces a phase delay. But by controlling the 2-color delay in the 2 beams separately, you can create fields that have always the same chirality in space. And with this field, you can enhance the response on one enantiomer and suppress it in the other. And by controlling this 2-color phase delay, you can create a locally chiral field that is always right-handed, or a locally chiral field that is always left-handed. And we saw some time ago that using these locally chiral fields, you can drive highly enantiosensitive high harmonic generation. So this is a very highly nonlinear process where the molecules absorb many photons from the field. Here we're looking at harmonic 40. And then they put this energy into one high energy photon. And we saw that by using this locally chiral light, we can drive ultrafast electronic currents inside the molecule, and these ultrafast electronic currents interact with the chiral molecular potential in a highly antisensitive way, giving rise to the emission in the right-handed molecule and no emission in the left-handed molecule. And of course, this can be controlled by controlling the chirality of the field. And yeah, I want to highlight the extremely important contributions to this work from Andres and also from Olga. I was a postdoc in Olga's group when we developed this. So I'm gonna show you now that with this setup, we can also do something that is fundamentally different. We can create locally chiral light that always has the same chirality in space, or we can create locally chiral light where the chirality changes. And we can control how it changes in space. And this is done, again, by controlling the two color phase delays between the two beams. I'm avoiding all technical details, but if you're interested, I can tell you more later. And when you look at this field, this is going to remind you of direct. This is a direct field, where you have left-handed field, right-handed field. Here, nothing in between. Left-handed field, right-handed field. So you have a repetition of units of direct fields. And we say that these fields have polarization of chirality in analogy with a polarization of charge. So you can have a dipole of electric charge by having a negative charge and a positive charge. Here you have left-handed field and right-handed field. And you can define a chirality pseudo-vector, a polarization of chirality pseudo-vector. So this is a dipole of chirality. And you can have a field that is left-handed and right-handed. And the pseudo-vector points like that. Or you can also have the opposite situation. And I'm going to show you now that these fields lead to different results when they interact with chiral molecules. Of course, this is not going to be useful for doing manipulation of chiral molecules or for doing photochemistry. This is the problem that Andres was describing. If you want to excite molecules with this field and look at the population that you have, that you excited, then you're going to excite here more of one enantiomer, but you will excite here more of the other. So I could think that these fields are not useful, but they are, if you look at nonlinear optical response. So with this kind of field, we can realize a chiral double slit experiment. So this chiral double slit experiment is as follows. You have the interaction of the locally chiral field with the molecules creates emission from the medium, and this emission can be understood as a contribution from two slits that emit from different positions. So in the two slits, you have non-chiral contribution, which is the same in the two slits, and chiral contribution, which is identical but has opposite phase. So the A chiral contribution to emission looks like this, which is symmetric with respect to this direction, because you have the same amplitude and the same phase. The non-chiral contribution, because it has opposite phase, it is odd with respect to this coordinate. So you have destructive interference in the middle, and then it's emitted with opposite phase. And when you put the two things together, what you have is that here you get destructive interference between this, and here you get constructive interference between this and this. So the result is that the emission of light is bent towards this direction. And of course, if you change the distribution of the slits, you get exactly the opposite result. You get that light is emitted like that. And these Gedanken experiments can be realized using light that has polarization of chirality and randomly oriented chiral molecules. So we did numerical simulations in randomly oriented tension, and we saw that if you have a field that has this structure of chirality, you have left-handed tension, then harmonic emission at this harmonic number is emitted preferentially to the left. But if you keep the same molecule, but then you change the polarization of chirality of the field, the molecules emit preferentially on the opposite direction. And you can change the direction of emission either by changing the polarization of chirality of your field or by changing the chirality of the molecules. We found recently that you can realize a similar experiment without chiral light, and if you're interested, I can tell you more later, but I don't have time. Olga is going to talk on Thursday about how you can structure chirality in a vortex and how this leads to robust and antisensitive observables. And I'm going to tell you about chirals and frequency generation. So the idea here is that we have shown that with this locally chiral light, you can drive highly antisensitive dynamics when you look at highly nonlinear process. But if you want to, at some point, start thinking of more practical applications, then it's going to be very beneficial to be able to drive equally strong antisensitivity at lower intensities. So for this, we need to bring these ideas to the perturbative regime. And to do this, we're going to start with something that is already very well known and established, which is chirals and frequency generation. This is a second-order nonlinear process where you have two beams that propagate in these two directions. They have this polarization at two different frequencies. And then the molecules, the medium, absorbs one photon from each beam, and then it puts this energy into a photon that is emitted somewhere in between. So basically, you absorb one photon from this beam, you absorb one photon from this beam, and then you emit one photon at the same frequency. So because of symmetry, this process is symmetry allowed only if the two frequencies are different. It can be very strong if we are close to resonance, and if it is emitted from the bulk, it is only symmetry allowed if the medium is chiral. So this is great because then you have nonlinear emission that is driven by pure electric dipole interactions that is exclusive of chiral media. The issue is that the intensity that opposite enantiomers emit is the same. The chirality is encoded in the phase of this signal. So if you want to know which chirality you have, you need to make this interfere with something else. And this can be done, this is done usually with two different approaches. You can either add an extra beam with the right frequency, which has the right polarization in the right direction, and then you can drive an anti-sensitive interference. But then, and yes, you have full control over the interference if you control the amplitude and phase of this beam, but you need to add a new beam, which complicates things a bit. The other option is create a non-chiral reference from the sample, and this is easier because you don't need to add a new beam, but then you have little control over the interference. So the question that we ask ourselves is, can we get the best of both worlds? Can we get an anti-sensitive signal without adding new frequencies, but also getting full control over this interference? So again, let me remind you, with this some frequency generation, you get one photon from this beam, one photon from this beam, and you emit frequency omega 3 in this direction, which has the same amplitude but opposite phase in opposite enantiomers. And as I said, you can have any combinations of frequencies as long as omega 1 is different from omega 2. But I'm going to impose that omega 2 is twice omega 1. And the reason that I'm doing this is that now I can get my non-chiral reference just by considering the next order nonlinear process, which is third harmonic generation. So the molecules can absorb 3 photons from this beam and emit a frequency omega 3. So this is going to be identical in opposite enantiomers in amplitude in phase. This is going to be identical in amplitude and with opposite phase. So by making them interfere, you can get an enantiosensitive intensity, although this is not working yet, and this is very clear if we consider momentum conservation. Some frequency generation, you get one photon from here, one photon from here, and then the emitted photon goes in between. Whereas in third harmonic generation, you get the 3 photons from this beam, and then the third harmonic is emitted co-propagating with this. So they don't spatially overlap. But we can make them overlap by adding the fundamental frequency also to the other beam. Because now we create new multi-photon pathways. Now we can get the 3 photons from here, the 3 photons from here, or we have mixed pathways where you get 1 from this and 2 from the other, or the other way around. And what's important is that one of these pathways leads to the emission of a non-chiral reference in the same direction and with the same frequency and with the same polarization as our chiral signal. And now we can make them interfere. And Jos and Laura did numerical simulations to show this effect, and this is the result. So this is the intensity of nonlinear emission in the far field as a function of the emission angle, and we see the 4 peaks that we already anticipated. And what's important is that this peak is very enantiosensitive. You get strong emission in the right-handed molecule, no emission in the left-handed molecule. And we can do this because by adding this fundamental frequency here, we are creating a locally chiral field. And of course, by controlling the 2-color delay, we control the chirality of the field, and we fully control this effect. So then you can select which enantiomer emits by controlling the 2 omega phase, because the 2 omega phase control the chirality of the field. And with this I finish. Yes, with locally chiral light, as Andres described, is highly efficient because it's chiral within the electric dipole approximation. We do not rely on magnetic interactions. We can drive ultra-fast electronic currents in the molecules that interact with the molecular potential in a highly anti-sensitive way, and we can structure this in space in order to, by controlling the beams that you use to create your light, you can structure it as you wish in space, basically, and you can control whether you have strong emission everywhere or whether emission is sent preferentially depending on the chirality in one direction or the other. And we don't rely on magnetic interactions, but we rely on nonlinear dynamics, and we can do this in the highly non-perturbative regime and drive high harmonic generation, or in the low order regime, and we require less, we require gentle intensities. And I believe that this creates very exciting opportunities for imaging, control, and manipulation of chiral molecules. Thank you very much for your attention.
Thank you. The talk is open for questions. No, there is no questions. You are tired. Okay, so let's thanks again, speaker and all the speakers of this session.